Now for the second type of improper integrals, integrals with infinite discontinuity or infinite range. Basically, those are the ones where we had that vertical asymptote in either the limits of integration or inside of the limits of integration. So if you have a vertical asymptote at x equals c, and c is somewhere in AB, so your vertical asymptote here is at c. Again, 3 different possibilities are happening. So here your vertical asymptote is at the upper limit of integration. You have to rewrite it as the limit as d approaches c from the left of the integral from a to d of f of x dx. Evaluate the definite integral and then evaluate the limit. Here, if your lower limit of integration is the vertical asymptote, then you make yourself the limit as d approaches c from the right of the integral from d to b of f of x dx. Again, first you evaluate the definite integral and then the limit statement. But notice that one of these was from the left and one of these is from the right. How do I know which to choose? Well, if your limit of integration has the vertical asymptote as your upper limit of integration, again, you're looking at a to c, and this guy is your vertical asymptote, the only way to get to c is to approach it with numbers that are smaller than c to approach it from the left. That's why we say from the left. And here, if your vertical asymptote is your lower limit of integration, so you're going from c to b, the only way to approach that vertical asymptote is from numbers that are bigger than c or from the right. So that's how you know whether to write the little plus sign for from the right or the little minus sign for from the left. The last one is just looking at if your vertical asymptote happens between a and b, you split yourself up over your vertical asymptote. And then, if you look at it, this guy here is the same as part A, and this guy here is the same as part B. One last thing before I talk about what happens when we find this limit. Recall, to find the vertical asymptote, you're going to set the denominator equal to 0 and solve for x. We're going to need to figure out where our vertical asymptote is when we're looking at improper integrals that have this infinite range or this infinite discontinuity, because if you don't know which one is your vertical asymptote, you don't know what number you need to be approaching and in what direction you need to be approaching that number. Now, just like the improper integrals that we saw that had the infinite domain, the same thing happens here. If the limit exists, the improper integral converges and the limit is the value of the improper integral. If the limit doesn't exist, then the improper integral diverges. So the nice thing is those don't change no matter what type of improper integral you have. Let's look at the last 3 examples in this section. We're still trying to determine whether the improper integral diverges or converges, and we evaluate the integral if it converges. With these, when you don't see positive or negative infinity with your limits of integration, you know automatically you got to figure out where your vertical asymptote is. How do you do that? Go to your function and look at the denominator. Well, the denominator in this first one in example 6 is just x, and you have to set that equal to 0 and then solve for x. Since I'm already solved for x, I know that my vertical asymptote here is going to happen at x equals 0. Then I grab a number line and I put my limits of integration. My limits of integration are from 0 to 1. Since this guy here is my vertical asymptote, I have to figure out, well, how can I approach 0? From the left or from the right? Well, from the right, because I can only approach it from numbers that are bigger than 0. That helps me find out how to do the limit statement. Now I know I can rewrite this as the limit as c approaches 0 from the right of the integral from c to 1 of 1 over x dx. So I need to figure out, am I approaching my vertical asymptote from the left or from the right? All you have to do is figure out which one is your vertical asymptote, draw that little number line, and then figure out if you're coming in from the right or coming in from the left. Now we need to evaluate the definite integral. This becomes the limit as c approaches 0 from the right of the natural log of the absolute value of x, and this gets evaluated from c to 1. Plug in the limits of integration. The limit as c goes to 0 from the right of the natural log of the outside value of 1 minus the natural log of the outside value of c. This guy here, the natural log of 1, cancels because we know that that guy is just 0. So the question is, as you're approaching 0 from the right, where is this guy going? Grab a graph. So if I go to my graph and I just look at the natural log of the absolute value of x. So again, here we have the natural log and then of the absolute value of x. So hit math, scroll 1 to number, hit enter for absolute value and put x. And then let's graph this. Well, as we approach it from the right of 0, well, the graph is going down towards negative infinity. And it's hard to see this from this graph, but this graph is continuing down towards negative infinity. It's going down towards negative infinity. So that means that this is equal to the negative of negative infinity, which is equal to positive infinity. So we end up getting positive infinity for the answer for the limit, and that means that my integral diverges. Number 7, I don't see a limit of integration that's positive or negative infinity, so this has to be one that has a vertical asymptote. Set the denominator equal to 0 to figure out where in the world you have a vertical asymptote. So here's my function. My denominator is that square root of 8 minus x. I set it equal to 0. If I square both sides, I get 8 minus x is equal to 0. If I move x over to the right-hand side, I get 8 is equal to x. So I know that that's where I have my vertical asymptote. Then I grab my number line, and then I put in a 0 and an 8. This guy over here, the 8, that's my vertical asymptote. The only way that I can get to 8 are from numbers that are smaller than 8, so I have to approach 8 from the left. Therefore, I say that I'm looking at the limit as c approaches 8 from the left of the integral from 0 to c, and then I'm going to rewrite this with a negative exponent so it's easier for us to integrate because it's not basic form. Therefore, this becomes 3 and then 8 minus x to the negative 1/2 dx. Well, let's use a u sub to work this out. If u is equal to the thing that's being raised to a power, 8 minus x, the derivative du would equal negative dx. Well, I don't have a negative dx, I have a 3 dx. If I multiply both sides by negative 3, I have negative 3 du is equal to a positive 3 dx. Therefore, I can say that this is equal to the limit as c goes to 8 from the left of the integral from x equals 0 to x equals c. And this just becomes u to the negative 1/2. And your 3 dx, remember, is that negative 3 du. If we integrate this, we end up with negative 3, and this is u to the 1/2 divided by 1/2, or 2u to the 1/2. I evaluated from x equals 0 to x equal, and I wrote 3 here, but I should have written x equals c. I do apologize. So that should be x equals c, not x equals 3. Getting out of u's, going back into x's, we're looking at the limit as c goes to 8 from the left of negative 6. And then instead of u, I know that's going to be the square root, and then that's just 8 minus x. And now let's plug in those limits of integration. So negative 6 square roots of 8 minus c minus a negative is plus 6 square roots of 8 minus 0. What happens when I plug in an 8? Well, when I plug in an 8, this becomes negative 6 square roots of 8 minus 8, and that's just going to be 0. And then this over here is just 6 square roots of 8, which I know the square root of 8 is really 2 square roots of 2. Therefore, I end up with 12 square roots of 2. That means that my limit is equal to 12 square roots of 2, and since my limit exists, I know that my integral converges. Let's look at the last one, the integral from 0 to pi over 2 of the secant of theta d theta. The first thing I need to do is figure out where is the vertical asymptote. Well, I don't have a denominator, but remember, the secant of theta is really just 1 over the cosine of theta, so your denominator is that cosine of theta. So you need to figure out, where does the cosine equal to 0 between 0 and pi over 2? Well, you know that that's going to happen at pi over 2. So if this is your number line, if this is 0 and this is pi over 2, the only way to approach pi over 2, where you have your vertical asymptote, is from numbers that are smaller, which means you're going in from the left. This then becomes the limit as c approaches pi over 2 from the left of the integral from 0 to pi over 2 of the secant of theta d theta. Well, this is basic form. If we integrate it, we end up with the natural log of the absolute value of the secant of theta plus the tangent of theta. Evaluated from, and I'm sorry, this here should have been a c. So this here is from 0 to c. Now, plug in the limits of integration. The limit as c goes to pi over 2 from the left of the natural log of the absolute value of the secant of c plus the tangent of c, and then minus the natural log of the absolute value of the secant of 0 plus the tangent of 0. Let's handle the easier one. The tangent of 0 I know is just equal to 0. The secant of 0 is equal to 1. So here, if I'm looking at the natural log of 1, I know that that guy just cancels because this whole thing is equal to 0. The only thing I need to concern myself about is this right here. Well, I can't find the secant of pi over 2 or the tangent of pi over 2 if I were to try on a calculator. If I were to just do 1 divided by the cosine of pi over 2, I know that I would get an error because I've been trying to divide by 0. So to find the solution, I need to plug in a number to the left of pi over 2. So what I'm going to do is rewrite this as a single fraction inside of the natural log first, to make it easier for myself when I'm plugging it into the calculator. I know secant is going to be 1 over the cosine, and I know that tangent is going to be sine over the cosine. What I'm going to do when I'm putting this in a calculator is just look at it as the natural log of the absolute value of the numerator, 1, plus the sine of c over the denominator, which is, well, the common denominator is cosine of c. And since I can't plug in a pi over 2, I need to figure out, give me a number to the left of pi over 2. So what is pi over 2? Well, pi over 2 is approximately 1.570796. So if I want a number that's to the left of pi over 2, I can plug in 1.5707. So plugging in a 1.5707, so you're looking at it as the natural log of the absolute value of 1 plus the sine of 1.5707 all over the cosine of 1.5707. Again, make sure that your calculator is in radians. So we say the natural log of the absolute value, which is math, scroll 1 over to the number and then enter, and then alpha y equals for that numerator and denominator, and we say 1 plus the sine, and we said 1.5707 divided by cosine of 1.5707. If you hit enter, you end up with a positive number. So what does that mean? That means that this is approaching positive infinity. So this guy here is approaching positive infinity. I know 9 is not a very big number, but it's positive, so that's all you need. Because if you were dividing by 0 and you looked at a limit that's one-sided, either from the left or from the right, then your graph is going towards positive or negative infinity. You just needed to figure which one it was. And in this case, we were looking at positive infinity, but positive infinity means that the limit doesn't exist. Therefore, we can just say that our integral diverges. That's it for improper integrals.